Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you. Most people have heard of phytoestrogens, but did you know there are beneficial phytoandrogens that mimic and support testosterone and more? The top source of these is pine pollen. If you're looking for 100% natural hormonal support for men and women, you've got to try this. Right now, Lost Empire Herbs' best-selling pine pollen is available for 1 penny plus shipping and handling. Go to geniuspollen.com to find out more and grab yourself a bag today. No hidden charges, no trial offer, no shenanigans. Just a low-cost way to try Lost Empire Herbs' top product for next to nothing.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do. But only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field. Sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have a really great guest, Dr. Omar A. He's a distinguished member of the technical staff. He's a chief scientist for the inertial confinement fusion program as part of the design physics DP division at Lawrence Livermore National Laboratory. And it appears they may have had a recent breakthrough, which I wanted to talk to him about in regards to fusion. So, Omar, thank you for coming.
Thank you for inviting me.
If you would, tell me a bit about your background, and then let's talk about your current work at Lawrence Livermore.
Well, let's see. So I'm a physicist by training and a mathematician. I'm actually fairly old now, but I've specialized in the area of what's called plasma physics, which is the physics of highly ionized gases. And I got hired by Lawrence Livermore National Lab almost 30 years ago to work on plasmas and national security issues that the laboratory is involved with.
So currently you're trying to make fusion work for at all, or for a certain application, or what's the outline of your current research?
Yeah, so a lot of people in the world have been studying fusion, making fusion in the laboratory since the 1950s, actually, using a variety of different techniques and machines. At our lab here, we use a giant laser system that was constructed, I think they started building it in the early 2000s or the late 1990s. It took a decade to build, a decade before that to plan, and then experiments started in earnest on it over about 12 years ago. And so all fusion research involves trying to mimic the reactions that go on in the center of the sun, where under large pressures and temperatures, you can take light elements, the periodic table in particular, hydrogen or isotopes of hydrogen, and combine them together under high temperatures and pressures, and they fuse together. They literally stick together, and they form larger elements, kind of going up the periodic table. And when they fuse, they liberate a bit of energy. And of course, that's how the sun, shines and makes the heat we feel here on Earth. That's how all the stars work. And the recognition of that fusion process was something that was recognized back in the 1920s and 30s. But at least at that time, no one had any ideas of how machines might be able to replicate that process here on Earth.
Right.
So I'm going to keep rambling if you don't stop me. So is that...
Quick question here. So what is the preferred starter fuels? Is it hydrogen?
That's a great question. So hydrogen is what the sun uses and is what stars pretty much use, because most of the universe is hydrogen. For us on Earth, though, hydrogen by itself does not make a very good fuel, because the fusion reactions that use hydrogen are actually really slow, and you need a star, a really big object that lasts for many millions and billions of years to get useful fusion energy out of it. So hydrogen does not work for us. The preferred fusion fuel here on Earth is an isotope of hydrogen, or two isotopes of hydrogen that are called deuterium and tritium. So deuterium is basically a hydrogen, which is a proton with an extra neutron stuck on it. So it's heavy hydrogen, or you've probably heard the term heavy water. And then a tritium atom is one where you have the proton with two neutrons stuck on it. So the most reactive fusion reaction that we know about here on Earth is what we call deuterium-tritium fusion, or DT fusion for short. And why that's preferred is to get the fusion to happen, it seems to require the least amount of energy of all the fusion reactions we know of, and actually has the potential to produce a lot more energy than you put in, whereas some of the other fusion reactions, and there are many others, will require more energy to make work, higher temperatures to make work, and you don't get quite as much energy as you would with DT fusion. So DT is what's preferred.
Could you use, I don't know, I guess you couldn't make a plasma with it, but could you use a soup of just protons and neutrons, one or the other as fuel, or would that, I'm just, again, armchair?
Yeah, so what makes fusion hard is, the nuclei of every atom has an electric charge, and a positive electric charge for the nuclei, which are with the protons. The protons carry the positive nuclear charge. The neutrons don't have any electric charge. And of course, the electrons, which surround the nuclei, is the negative charge. So why fusion is hard is you have to kind of bring these nuclei together, and that's why we need high temperatures and high pressures. And because the nuclei have positive charge, they tend to repel each other. And so you have to overcome that electric repulsion. So in principle, if you can overcome that electric repulsion, you can combine any atoms together, but the more electric charge the atoms have, the harder it is to bring them together. And so that's why, hydrogen is preferred by Mother Nature and stars, and deuterium and tritium is preferred by us here on Earth. Stars are capable of fusing elements higher up the periodic table, carbon, for example, and oxygen, but that's pretty hard for us to do here on Earth. So we tend to want to go far down on the periodic table as possible for practical fusion on Earth.
Are there any elements that you could bombard with, either protons or neutrons, and they're close, let's say, to a stable state, and
so you can
one more proton to stick, it would work?
Yeah, you can actually bombard targets with a beam of protons or neutrons, but energetically that doesn't work out mathematically for creating net energy. You can get fusion to happen, but you'll end up spending a lot more energy to make it happen than you'll ever get out. So the idea of using a target with a beam, like an accelerator, to make fusion was studied, and I think that was back in the 1950s or 60s, and it doesn't add up. The math doesn't add up. The problem is when you accelerate particles that have a charge to high velocities, as is needed to get fusion to happen, they tend to radiate a lot of energy away, and it's hard to make up for that radiation energy loss.
I see. What about using some kind of controlled fission to then accomplish fusion? Is that a possible path?
That's a possible path, but generally people don't like, I mean, obviously fission is something that's used in fission reactors, and that's a technology we know. People who are working on fusion are actually trying to avoid fission, because that tends to create a lot of actinides and radioactive byproducts that, we just prefer to avoid. But in principle, fission can make things easier if you wanted to include that step.
Yeah, it's just pure speculation, but I wonder if existing nuclear plants could add on, let's say, a fusion component somehow, and they could use the energy produced from the fission to somehow power fusion. Just a thought.
I have to be careful, because that's combining fission and fusion, starts to cross into some national security topics.
Oh, really?
So I have to be careful about how I answer those
Well,
questions.
I'll end my speculation
So,
here then.
yeah.
That's fine. No problem.
Otherwise, the men in black will show up and cart us both away. That's
Well, yeah. What can you say about the actual fusion process? So you're starting with deuterium or tritium, and
Yeah.
how does the whole thing work?
Yeah, so the neat part about deuterium-tritium fusion is the reaction rate rapidly increases with temperature. And so the idea is if you can make DT fusion happen and it liberates some energy, if you are able to engineer your system such that you can hold on to a little bit of that energy and retain it, that would cause the plasma that you're using to make the fusion energy happen a little hotter. But as I just said, the DT fusion reaction rate goes up with temperature. So if we can make the DT fusion reaction system a bit hotter, we'll get even more reactions out of it. And if we could retain some of that energy, we can make it hotter yet. And that will further increase the fusion reaction rate. So the idea behind DT fusion is this process that we call, quote, bootstrapping, where as the fusion reaction goes on, if we can create the conditions where we could retain some energy from the fusion reactions, it gets hotter, that increases the reaction rate, it gets hotter yet, it creates even more reactions, and the process just ramps up very rapidly, and you can get a very large liberation of energy, which is reflected in very large temperatures and very large energy outputs very rapidly. So that's what we're after. That process we tend to call bootstrapping, where the fusion heats itself and then Mother Nature just takes over for you. So that's what we spend a lot of time trying to do, is engineer with our devices a condition such that we can create enough fusion to get the whole thing started and then retain some of that energy that comes out to get the thing to self-heat. The byproducts of the DT fusion, which I didn't mention previously, are an alpha particle, which is a helium nuclei, and a neutron. So when you get the DT fusion to fuse together, the DT atoms to fuse together and liberate energy, the energy comes out in the form of 20% going into this alpha particle or helium nuclei flying outwards, and a neutron carrying 80% of the energy flying outwards. So what we try to do in our systems, and most of the people working on DT fusion across the world, you try to arrange it such that that alpha particle that carries 20% of the energy is stuck inside the plasma that's generating the fusion. And if it's stuck well enough, that 20% of the energy then goes into reheating the plasma that generated it in the first place. The neutrons just keep flying outwards, and that's basically how you get the heat out of the system. So that alpha particle, the way you can get it to leave its energy behind, there are a number of different things you can do. You can create conditions that are dense enough so that that alpha particle will bang into other atoms, and that will basically heat the system. You make the system large enough, the helium atom will eventually bang into something and leave the heat behind, or you add magnetic fields such that because the helium has a charged nuclei of 2 protons and 2 neutrons, it will just be trapped by the magnetic field, and it will circulate around, and it will eventually bang into something, leaving the energy behind. So what we try to do is create enough density or enough size of our system, or add magnetic fields or some combination of any of those, such that you can trap these alpha particles to get the energy left behind. And if you do all that well enough, you get this bootstrapping self-heating process, which is where you have the potential to get more energy out of your fusion system than you put in. The difficulty is it's really hard to get the conditions needed for that to happen. And so for decades, people across the world have been trying to design things and do the experiments that allow us to hold on to those alpha particles. And Mother Nature has a bunch of tricks that she throws at us to try to undo what we're trying to do.
Most supplements are taken on faith and can take weeks or months to have an effect. Even supplements backed by scientific studies may or may not deliver those same benefits to you. But what if you could feel the results of what you took within just a few days? Lost Empire Herbs offers the highest quality, wild-harvested, non-irradiated pine pollen, and that can dramatically impact your hormones fast. Right now, you can grab it for 1 cent plus shipping and handling at geniuspollen.com.
Well, can we go a little deeper? I was in a comment before we move on. It's interesting. I learned from one physicist that I guess larger nuclei, they have a substructure which appears to be like helium nuclei. So a nucleus, let's say, of a gold atom. I guess from what I've heard, it appears to be a bunch of like helium nuclei substructures in the nucleus, or helium-like, clusters
basically,
of neutrons.
when you go high up on the periodic table, these are very large nuclei with a lot of protons and a whole lot of neutrons. Those can be broken down into smaller and smaller sets of protons and neutrons, and that's how you go down on the periodic table. So everything's basically built of hydrogen, and the next step up is helium, but you can keep combining these things together, and that's how you make the entire periodic table, where you have very large nuclei like gold, or even higher up on the periodic table is uranium. So everything that every atom in the universe is basically built from those simple atomic structures.
Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button, and we'll be able to solicit donations to help keep the podcast running, and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up, and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Yeah, it's just interesting because in fusion, that's one of the major byproducts you're getting, and that kind of, I guess, hints at the provenance maybe of larger elements, that they were created by fusion inside of stars.
Yeah,
because they would have been built from the the helium nuclei.
Yeah, that process, which I think is called stellar nucleosynthesis, that was actually identified, I think, in 1929, maybe 1930, by a famous physicist whose name is Hans Bethe. He's gone now, but he's the one who understood or developed the physics of the process that goes on in stars called the stellar nucleosynthesis, where he figured out how all these fusion reactions occur to build every element in the periodic table. And so all the elements that we have here on Earth that we make things out of were all at one point built in stars through a fusion process. And then the stars blew up. That multitude of different elements gets cast into space and forms planets, and then life develops on the planets, and here we are.
So going back to the fusion reaction, you just spoke about high temperatures. So what kind of temperatures are we talking about, and what's necessary to achieve the temperatures we need?
Yeah, so that's a good question. So, we tend to use a unit of temperature called a kilo-electron volt. And so we are generally trying to achieve temperatures, over 5 to 10 kilo-electron volts. Now, the kilo-electron volt doesn't mean much to most people who don't work in the field. So 1 electron volt is 11,600 Kelvin. And so, 10 kilo-electron volts, which is kind of a target temperature that we try to get to, is something like 100 million degrees Kelvin. So it's super hot. And then within a factor of 2, most of the people working on DT fusion are trying to achieve that sort of temperature. So it's really quite hot. And for example, if Kelvin doesn't quite resonate with you, although you can Google it, the surface of the sun is over 5,000 degrees Kelvin. So it's much, much hotter than the surface of the sun. Yeah.
How do you keep this high temperature away from the walls? It would melt everything. Things melt not just because of temperature, but because of heat, energy content. So if you have a very low density plasma at a very high temperature, it may not necessarily melt the walls. But yeah, you're right. We do want to keep these things away from the walls of a chamber. So the people who work on magnetic fusion, they use these magnetic fields to basically create an insulating layer
of magnetic field between the plasma with the high temperature where they're trying to make fusion happen and the wall of the device, which if the plasma hit that wall, it would actually quench the plasma and could damage the wall. For us who are doing inertial confinement fusion, what we have is a target which is at the center of our target chamber, which is about 5 or 10 meters away from the walls of our chambers, and it's basically suspended in space, and we're blasting it with these laser beams to try to generate the high pressures and temperatures that are needed. So it's really just stood off from the walls by a sizable distance, and the temperatures and densities are created in a very small volume well away from those walls, yeah.
So why does everyone keep saying, oh, fusion is, decades away? I mean, how much progress has been made, and why does it seem so elusive and so difficult to accomplish?
Yeah, we basically, in addition to the high temperatures, which we just mentioned, we're trying to generate very high pressures, at least in inertial confinement fusion. We have to get pressures that are larger than the pressures at the center of the sun. And our recent experiment basically is over twice the pressure at the center of the sun. And, that's just not easy to do. People who, work on magnetic fusion, they aren't trying to generate super high pressures. They're usually trying to generate pressures of just, 2 or 3 or 4 atmospheres of pressure. But they do need to get these high temperatures. Their problem is that they have to hold on to this plasma for a very long time to give the reactions a chance to occur. And Mother Nature really doesn't like putting a lot of energy and a lot of temperature in a small volume. She creates these things that we call instabilities that try to cool things off, and wherever you have a density gradient of material, she tries to flip the densities around. So where you have high density up against low density, she tries to make them change places so that everything gets evened out. So Mother Nature wants everything to be smooth and cool, and so we're constantly fighting her to try to create the conditions that were needed, and that's just very hard to do. So it has taken decades. I think people were probably overly optimistic. People working in the field were overly optimistic early on, and the number of instabilities that occur in plasmas where Mother Nature is trying to undo your heating and compressing of the fuel, actually they're quite ubiquitous. There are quite a number of these different instabilities that she throws at you. And every time you think you've solved one, something else comes up. So it's just been hard. And it has taken decades since people first started working on fusion. But there actually has been steady progress. The problem with the perception is it's kind of been a very slow evolutionary progress rather than someone just kind of hitting a home run and all of a sudden all problems are solved. And, that is why I think people have this perception. Nevertheless, progress has been made over these decades. People in magnetic fusion, a key metric they use is called the confinement time. Their confinement time for magnetic fusion has increased over many orders of magnitude over several decades. For us, our metrics are these, pressures and temperatures. And again, for us working over the last 10 years, we have increased the performance of our experiments in terms of fusion yield by a factor of 1,000. So, but it's a slog rather than a home run to win here.
So what are some of the KPIs or metrics that would tell you that it's successful and viable, and how far away are we on some of the metrics?
Yeah, so a key metric that's used in fusion is something that's called the Lawson condition. And Lawson was a physicist who developed some of the ideas behind what's needed for practical fusion energy. He did this back in the 1950s. And the Lawson condition is basically a product of pressure, temperature, and time. And there are variations on it that are more complicated, but that's a pretty good metric. So the plasma conditions behind that metric, or the physical statement behind that metric, actually more correctly, is that for a process called ignition to occur, which is that bootstrapping process where the reaction just kind of rapidly heats itself, like I described earlier, we call that ignition. And Lawson's physics statement about what that condition is that, well, the heating of the plasma has to outstrip all the processes that want to cool the plasma off. And so the heating process we discussed, it's this, we make fusion. When fusion happens, you get some heat out, and if you can hold on to that heat, you get more heating. And we call that self-heating process alpha heating. So if that wins out over all the cooling processes, you can kind of get ignition. Problem with a plasma is there are a whole bunch of cooling processes. There's these instabilities, which I discussed earlier. You have heat conduction, where if you have a high temperature next to a low temperature, whatever the material is, heat likes to go from high temperature to low temperature. You get close to an oven, you can feel the heat radiating towards you. So that's one process that cools a plasma. Another process is radiation. When you have a plasma, you have all these charged particles flying around very rapidly because the temperatures are high. And there's this property of charged particles that they tend to create radiation in terms of X-rays, or visible, in some cases, radiation that carries energy away. And so all these plasmas are constantly radiating energy away as we're trying to get them hot. And also in the case of an inertial confinement fusion plasma, because we're generating these super high pressures in a small volume, they tend to blow themselves apart very, very rapidly, and that creates another loss of energy that we term PDV work. It's basically the volume expansion carries energy away. So you have all these processes that are trying to cool things off. You have that one alpha heating process trying to make things hot, and you only win if the alpha heating process beats everything else, and that's Lawson's physics statement. That turns into, when you do the math, it turns into a product of pressure, temperature, and time. So that metric we've increased, at least here in our lab, by a factor of 50 or so since we first started. So that's a dramatic advance. And right now, the big advance that you contacted us about and wanted to talk about today is how we're kind of at the threshold that Lawson identified as being important for achieving ignition. So I gotta be careful. I'm going to keep rambling.
No problem. Yeah, can you give a few details? What is the current breakthrough, just in layman's terms? What have you figured out?
Well, basically, again, there was no kind of dramatic home run that we've done to suddenly cross into this threshold. What it's been is a process of incrementally identifying problems and fixing them over a period of the last decade to try to tilt this balance of cooling and heating in favor of heating. So, when we started 12 years ago, the cooling processes were just swamping everything. And it was, things were not working very well. What we've learned is, we have to try to control instabilities, hydrodynamic instabilities in our implosions better than we thought we needed to. And that allows us to get to higher densities and temperatures. We've learned that, we have to control the symmetry of our implosions better than we were originally. And that allows us to take better use of the energy we put in to our implosion to generate the conditions of pressure and temperature that are needed to achieve nice fusion conditions. So it's basically an efficiency improvement by making the implosions more symmetric. We've learned that if we can leave the laser on later in time, even if we have to lower the power in our system, the late time environment around our implosion matters a lot. So if we can keep the pressure on the outside of our implosion later in time longer, tend to be more successful. So it's been a whole process of steps of learning what we need to do on the physics side to try to incrementally increase temperature, pressure, and time. And we've done it, again, kind of over a decade and kind of crept up on this Lawson boundary. At the same time, the engineering of our targets and the engineering of the laser are also not fully known. So those are research and development efforts in themselves. So we learned that, the targets quality we had originally wasn't the best. So we've learned that we need to improve the quality of certain aspects of our target, and that just takes time for the material scientists and the engineers to do that and figure out what the new processes need to be, and it needs to be consistent with what we need on the physics side. We've learned the laser, it needs better control of for the NIF laser, which is the National Ignition Facility here at Livermore. There are 192 laser beams. They all have to be synchronized to shoot our target, and there's a temporal pulse of laser power versus time that's on each laser beam. They have to be synchronized, and it has to arrive at the target at the same time to within 50 or so picoseconds. And that's hard. And so we've had to learn that we can't allow several hundred picosecond asynchrony between those different laser beams. So that had to be tightened up, and how to make the laser do that has been a lot of effort. The laser also has to have these rather precise jumps in power up and down to allow us to compress the target to sufficient density while still keeping it cool. And that takes precision control of the laser to do that, and it takes time on the physics side to try to engineer what those jumps in the laser power need to be, such that we can first assemble our compressed fuel into high density and then make it hot, rather than basically trying to make it hot and then compress it, which then makes the compression pretty much impossible. So it's been a lot of learning, and on across the laser engineering, target engineering, physics side, and it's iterative because you fix one thing, you screw up something else, and that just took a long time to sort all that out.
Are there any quantum effects? I mean, from what I've heard, the reason why the sun shines and we can see it is based on quantum effects, but I think most people would think quantum effects only happen, again, when things are very cool, not when they're very hot. But
well,
do you
when
experience any of that?
Yeah, so we do have to worry about atomic effects. So the radiation of our plasma is an atomic effect, and when you bring these nuclei close together, the reason they fuse is a nuclear quantum effect, so to speak, that brings them together. So it's scale, but most of the atomic physics was worked out again kind of back in the 20s and 30s. So as part of our job, we don't generally think about quantum effects explicitly in the work we do. So
okay. I know it's going to be a while for more breakthroughs. It seems like a very slow process that, again, takes years and years and years. What possible expectations do you have over the next maybe a couple of years? Is it just going to be a continual slow march forward, or any breakthroughs coming, you think?
I think so. Again, it's more of an evolutionary process than a revolutionary process. What's exciting about our result illustrates an existence proof that we can actually make ignition happen in the laboratory. And that was not guaranteed, because until you actually do it, there's quite a lot of skepticism that we might not ever be able to do it. And so now we basically have an existence proof that ignition in the lab is possible. So at least we can check the box on that. But the fact that we've demonstrated that doesn't mean that all of a sudden it's practical. So we are certainly still struggling to try to improve our fusion process to get a lot more energy out than we put in, and only until we can really kind of extend that quite a ways is it going to start looking practical for a variety of different uses. I should say here at our lab, we're a national security lab, so actually this whole process of just learning how to make it work and testing our experiments against our computer models and our understanding is part of our mission, because we're supposed to be experts in this area, and we're responsible for the nation's nuclear stockpile as well. So we're supposed to be able to understand this stuff and predict it well. And there's an old saying by one of our old directors that in the absence of experiments, confidence goes up and competence goes down. So part of what we're doing is just doing the experiments so that we can maintain a high level of confidence and not be overly confident. So we're already kind of doing that job by going through these processes and wrestling with Mother Nature, but we want to keep extending what we're doing to higher levels of performance and learn what we need to do about the engineering and the physics to try to squeeze as much out of it as possible over time.
Yeah, it makes a lot of sense. Where can people go to find out more about fusion in general and about what you're working on at Lawrence Livermore or whatever they have on their website? What's the best place?
Yeah, so I think we have a web page that's available so they can learn about what we're doing. So we have a web page. You can go to lasers.llnl.gov, and you can learn about what we're doing, the National Ignition Facility laser, and there are a bunch of different menus where you can learn about the experiments, see images, see pictures, and read about our accomplishments. Other laboratories that work in this area are Princeton Plasma Physics Lab. They're trying to do magnetic fusion, but they're another good resource for education. I think their website is www.pppl.gov. you might have to double check that.
Unless-
Michael, do you know of another? I was trying to find on our webpage where we have all those stories about what we've done.
Yeah, we can get that at the end.
I think you covered it, Omar.
Okay, super.
Yeah, Omar, I just have one last question, if that's okay. Do you need to just get a very small positive amount of energy coming out of the system and just letting it run and run and run? Or do you need a substantial amount of energy coming out so that the system doesn't have to run for very long times to produce, quote unquote, enough energy?
Yeah, so for us, no, there's a difference. For inertial confinement fusion, it is naturally impulsive. So there is no avoiding putting energy in, getting your conditions through this thing called an implosion, which gets you the density, temperature, and pressure, and then it blows itself apart and liberates energy in that process. What we want is to have more energy coming out of the fusion process than we put in from the beginning. And that, for us, that just requires more and more extreme conditions to get a more extreme bang and liberation of energy. For magnetic fusion, that is the one where you try to put in a minimal amount of energy at the beginning, and if you can design the conditions well enough, you can then take away your external sources of heating, and the system will just kind of keep heating itself, and that will run and run and run. So magnetic fusion is basically quasi-steady state in time, whereas inertial confinement fusion is by its nature impulsive. And the way you vision getting a lot of energy out over time is you basically do that impulsive thing over and over and over again, kind of like the explosions in the cylinder of an engine of an internal combustion car. You basically, you're banging a little bit of gas that's mixed with fuel. It pushes the cylinder down, and you do that over and over again. It makes your car go in a semi-continuous fashion. So it's basically two different ways of doing it. But the ultimate goal is you try to get out more energy than you needed to put in the first place, and that's when all of a sudden it becomes practical and goes from being a research project to something the average person might be interested in.
Oh, so you get out, like, I guess, somewhat discrete bits of bonus energy, and you want to drive the reaction trillions or quadrillions of times a second.
Yeah, you just do not that many. I think for inertial confinement fusion, the energy scheme for inertial confinement fusion is called inertial fusion energy, and there what people envision is that you might do these bangs several times a second. People quoted things like 10 times a second to get the repetitiveness that's needed to drive energy on the grid, but that's kind of speculative at the moment.
Okay. Well, very good. Omar, thank you so much for talking about this. It's a really interesting subject, and I appreciate you being on the podcast.
Okay, well, it was my pleasure talking to you. Thank you.
Remember, before you go, to grab your 1 penny bag of pine pollen for all the amazing, all-natural hormonal support that men and women the world over are raving about. Try it out and see how it works for you. All you have to do is head to geniuspollen.com to grab your bag today. Within days, you may be able to notice greater energy, more focus, added recovery, and more. Again, please visit geniuspollen.com to learn more now. Thank you.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.